Hello everyone, this is Dr. Hopkins narrating the next video, and this is our first in our chemical kinetics videos where we're going to do a little bit of Gen Chem review, or 106, 107 review. Alright, so we're going to start with the definition of chemical kinetics. We're looking at the time dependence of reactions, and now kinetics is an almost entirely empirical kind of measurement or science, if you will. There are some, now we are capable of calculating reaction rates these days, but for the most part, if you want to know how fast a reaction runs, you have to measure it. So we're going to start with a general reaction of just A to B. We could expand the number of products and reactants and easily expand these terms. So the rate of the reaction, and there's only one rate of a reaction, so the rate of this reaction can be related to the rate of disappearance of the reactant, and we have to have a stoichiometric coefficient, or the rate of appearance of the product. So in some sense, if we want to measure how fast a reaction goes, we can decide which one is easiest to follow. Alright, so when we have a reaction, we have kinetics, we can express the concentration dependence of, say, the reaction or of the reactant in terms of a rate law. So that rate, which we would have just a rate of reaction, it could be the rate of disappearance, rate of appearance, is equal to K times the concentration of our reactant. So if we increase the reactant, we might increase the rate. And then we have an X, which is an order. So we have the rate is in molar per second. K is our rate constant, is independent of concentration. It does depend on other factors like temperature and so forth. And the units for K, it depends on X because our rate always has to be molar per second. And then X is the order of the reaction. So it can be any number, 0.5, 3, 3000, whatever it might be. All right, so we have a couple of rules in terms of rate laws. So reactions don't have to have integral orders. So they don't have to be first order. They don't have to be second order. The reaction order for reaction doesn't have to be well defined. So over the course of a reaction, the order can actually change. And then also the reaction order almost never reflects the stoichiometry of the reaction, unless we're talking about a particular type of reaction like an elementary reaction. And then, as I stated, the rate constants are independent of concentration. So let's take an example reaction. Here is some gas phase reaction, decomposition from reactant to two products. The rate law, we're going to write the rate in terms of the rate of disappearance of the reactant, and it has a rate constant units because of the order of the reaction. So this is a 3/2 order, so 1.5 order reaction. So obviously that doesn't have to be integral. So that would be how we'd write a rate law. If we wanted to increase the reaction, we'd just increase the rate, we'd just increase the concentration. Or if we look at the evolution of the reaction, it's going to slow down as the concentration of the reactants decreases. So if you have multiple, now so far all we've dealt with are reactions with one reactant. If we had multiple reactants or multiple components in our rate law, the overall order of the reaction is just the sum of those, and then that would be how you determine your rate constant. And then importantly, rate laws, one, they're a measure of reaction rates, which is great, but they also are a way of helping determine the reaction mechanism. So in other words, you can't really understand the mechanism of a reaction without measuring its rate law. So, and a reaction mechanism, as you may or may not remember from organic chemistry, is just a series of steps from reactants to products. Okay, so the process it goes through. All right. So reaction mechanism, so we're going to talk a little bit about this. We will get to more of this as we go on. This is just our review. So each step in a mechanism is called an elementary reaction, and then kind of in a circular definition, the elementary reactions are their own mechanism. So they're just telling you what two molecules or what one molecule must do to form products, basically. And then each elementary reaction has a molecularity. That's the order of the elementary reaction. And so an elementary reaction is the one case where we can look at the stoichiometry and determine the order. So for example, if we have a unimolecular reaction, so A to P, so we have one here in front of this, we know this is first order, and we would write the rate law as K times this A. If we had a bimolecular process, so if we had a bimolecular of two of the same component, the rate law is second order in just A. If it's bimolecular in two different components, it must come together to form product. Then it's the rate law A times B. So it's first order in each of these components, but second order overall. And the last one is trimolecular. Now we could keep going up, but trimolecular is very rare because it's very difficult to get three reactants in one space to form one reaction at a time. So typically most of your steps are either unimolecular or bimolecular. All right, so then if we have this rate law, we can actually take, since those are the change in concentration over change in time, those are differentials, we can integrate the rate law in order to determine the concentration of any of our components at any time t, which is a very powerful thing. And so what we're going to talk about is how to do integrated rate laws. So let's consider this just general reaction. If we consider its rate its first order, I'm going to write the rate as the rate of disappearance of the reactant, so dA over dt. So this is a simple first order differential equation. So we'll just separate our variables. So we'll put our a's on this side and our t's on this side. And then we will integrate from our starting concentration to whatever concentration at time t. Starting time is 0 to time t. If we do that, we get this is the natural log of these limits, and this is just dt, so it's t. And so we get this natural log of this ratio equals minus kt, or if we write it in a more familiar Gen Chem term, the natural log of the concentration at any time is equal to minus kt plus the natural log of our starting concentration. So if we were to plot natural log of concentration versus time, it would give a straight line if it were first order. And we can do this, excuse me, and so then if we're looking at the concentration at any time, so we know that the A of t is just our initial concentration and an exponential decay with respect to the rate constant. So if we started with all of A, so we only started with A, and had none of the product to start with, then everything must sum to the original concentration of A, our concentrations. So we know that this is the case, and then we can decide, well, the product concentration at any time t is just our original concentration 1 minus an exponential decay. So we can figure out our product concentration at any time t. We can figure out our reactant concentration at any time t. So we know what everything's happening. And then in first order, we could do a half-life. So this is an important kind of concept that you did in general chemistry and from kinetics. So the time to get to cut your reactants in half. In a first order reaction, it is independent of concentration, so it's just natural log of 2 over the rate constant. We can do the same thing, so we're not going to go through the exact integration for all of the other order reactions, but you could do the same thing for second order of this type, where we have second order in one component. If we split up and integrate that, we would end up with a 1 over a kt. So then if we were to plot 1 over a versus time and it's linear, you get basically you're showing that it's second order. That's something you did in general chemistry. But our concentration at any time t is related to this. And then our half-life, now in a second order reaction, our half-life does depend on our initial concentration, unlike first order. So that's one differentiating feature between second order and first order. So let's look at something you didn't do in general chemistry, which is look at the rate constants of a second order reaction where you have one of first order in two different components, which is a lot more common than just combining one component into making monomers into a dimer or something like that. So we have this rate law, okay, first order in A and B. And so I'm not going to show the integration because it requires a little algebraic and manipulation. You have to assume some initial concentrations, but it is it's a natural log, so it is a first order in each component, so it's a natural log of the ratios versus t, and the natural log of our initial concentration. So if we were to plot our natural log of our ratio versus t, we could figure out our rate constant, our second order rate constant. Now, what's often done to determine the reaction kinetics for these types of reactions is that you make one of the components, say A or B, let's say B, let's add this reactant in such excess that it's not going to change over the course of the reaction. So it's so much larger that we're really not going to reduce it at all. And this makes the reaction pseudo first order. So if we start with, we'll remanipulate this equation. So KT, so we have this ratio. And then if we realize that B is in great excess, this ratio never changes. So that's 1. So B0 and BT are always the same. And so then our expression is the natural log of A over A0 is equal to this KT. Okay, now if we were to look at this linearly, this would be natural log of A equals minus this component KT. Now we know that B is much larger than A, so we can get rid of this, and so all of this slope of a plot of natural log of A versus T would be the initial concentration of B, our large concentration, our second order rate constant times T. Or if we combine those together, you get what is a pseudo first order rate constant, okay, which you can pull out because if you know how much B you started with, you can pull out the original second order rate constant. But this is an example because kinetics is so empirical that you can manipulate how you measure the kinetics by manipulating your reaction. And so until next time.